Okay, in this lesson we're going to look at rational functions of the form f of x equals ax plus b over cx plus d. Now these rational functions are a little bit more unique than the ones that you've seen so far. And in these rational functions what you'll notice is that the degree of the polynomial in the numerator and the degree of the polynomial in the denominator are exactly the same. So for example, you're either going to have a linear expression over a linear expression, or you'll have a quadratic over a quadratic. So basically the numerator and denominator will have the exact same degree function present. And so these rational functions, because they're a little bit different than what you've seen so far, there will be some changes in the asymptote. Namely, the horizontal asymptote will be much different than what you've seen so far. And so as a result, some of the domain and ranges will change as well. So we're going to focus on the horizontal asymptote for these functions first. And so one way to examine these horizontal asymptotes is to divide the numerator and denominator by x and then examine the end behavior of the function as a result. Okay, so let's say you have a function like g of x equals negative 3x plus 1 over 2x plus 1. So you have a linear function over a linear function. Now in this case, when you're trying to figure out the vertical asymptote is still the same. You would solve for the vertical asymptote in the same way you did before. So you'd say the vertical asymptote is x equals negative a half. But the horizontal asymptote is no longer y equals 0. The horizontal asymptote in this case is actually something different. And so just like we talked about before, the end behaviors of a function sort of give you an idea of what the horizontal asymptote would be and whether the asymptote is being approached from above or below. And so when you have a function where the degree in the numerator and denominator are the same, so linear over linear, what you could do is to divide both sides by x, divide the numerator and denominator by x, much like what we've done here. So there's a numerator divided by x, and there's a denominator divided by x as well. And if you simplify that, what you end up with is negative 3x over x is negative 3, 1 over x is 1 over x, and then 2x over x is 2, and 1 over x is 1 over x. And so think about what happens if you plug in very, very, very large numbers for x or very, very, very small numbers for x. What ends up happening to this term here in the numerator is that it starts to approach 0. So it ends up being very negligible in comparison to that negative 3. So if I plug in a very large value for x, like 100,000, this will be a very, very small number. Okay. Similarly, in the denominator, if I plug in a very large number for x, like 100,000, or a very, very small number like negative 100,000, the same thing's going to happen here. This part here is going to be very negligible, and so it's going to be approaching 0. So what ends up happening is the function at the two ends of the graph starts to approach just the coefficients of what you used to have for x. Okay, so it starts to approach just the coefficients that were here, which is in this case negative 3 over 2. Okay, so what happens when you're looking at functions where the degree in the numerator and denominator are exactly the same is the function horizontally starts to approach the value of the coefficient in the numerator divided by the value of the coefficient in the denominator. So in this case, the horizontal asymptote ends up being negative 3 over 2. Okay, so that's the important change that ends up happening when you have rational functions with the same degree polynomial in the numerator and denominator. When you are graphing a rational function, the following key features of the graph must be included. And this is true for any of the rational functions that we've seen so far. We need to know the asymptote, so the vertical asymptote and the horizontal asymptote. We want to look at the behavior close to the asymptote. So for vertical asymptote, you want to see what happens as the function approaches a vertical asymptote from the left and from the right. So you want to see whether it's approaching positive infinity or if it's approaching negative infinity. And then for horizontal asymptotes, you want to examine end behaviors to see whether the function is approaching the asymptote from above or from below. Okay, and then finally we want to look at the x and y intercepts as well. Okay, so we're going to look at an example. And the example says, consider the function f of x equals x over 2x plus 5. So you'll notice that you have a linear function in the numerator as well as a linear function in the denominator. So we're going to look at the equation of the asymptotes and then the domain and range. We'll look at the behavior of the function near all the asymptotes, so near the vertical asymptote and the horizontal asymptotes. And then we'll look at the x and y intercepts, sketch a graph of the function, and then describe where the function is increasing or decreasing. So that's the part that we haven't seen in too much detail yet. Okay, so we'll look at this example. So I wrote down the example on a separate sheet of paper so far. And so we'll start with the asymptote, starting with the vertical asymptote. And the vertical asymptote occurs based on any value of x that will make the denominator 0. And in this case, that's negative 5 over 2. Okay, or negative 2.5. So x equals negative 2.5. And then the horizontal asymptote, in this case, because the degree of the numerator and denominator is the same, you want to look at the coefficient of the x in the numerator and the coefficient of the x in the denominator. And so there's an imaginary 1 at the front here. So what that tells me is that the horizontal asymptote is at y equals a half, or y equal to 0.5. Okay, so we're looking at the coefficient of x in the numerator and denominator to help us figure out the horizontal asymptote. And then the domain and range is based on whatever any of the restrictions are on the value of x and the value of y. So in terms of domain, x is an element of all real numbers such that x cannot equal negative 2.5 or negative 5 over 2. And for the range, y is an element of all real numbers such that y cannot equal a half or 0.5. Okay, in terms of the behavior near the asymptotes, so we'll start by looking at the vertical asymptote. So we're going to look at the behavior of the function as it approaches negative 2.5 from the right and negative 2.5 from the left. And then we'll look at what happens as the function approaches positive infinity and negative infinity. So the end behaviors of the function as well. Okay. So I'm going to choose a value of x that's slightly to the right of negative 2.5. So I'll choose something that's to the right of it. So maybe something like negative 2.49. And so if I try to solve for f of negative 2.49, and I type that into my calculator, I get about negative 124.5. Okay, so what that tells me is that the function is decreasing, and so it must be decreasing towards negative infinity. Okay. Similarly, if I plug in a number that's a little bit to the left of negative 2.5, so if I look at negative 2.51, and if I evaluate the function at that point, I get an answer of about 125.5. So positive 125.5 tells me that the function is increasing, and so it's probably approaching positive infinity. Okay, finally, I'm going to look at the function at the end behavior. So I'm going to look at what happens to the function as I approach a really large number for x and a really small number for x. And so I'll look at the function at a value of 1,000 and the function at a value of negative 1,000. And so when I plug in 1,000, I get an answer of about 0.4987. Okay, and when I plug in negative 1,000, I get an answer of 0.50125. So if you examine what's going on here, you'll notice that it's no longer getting close to 0. Now it's actually getting closer to 0.5 because that's where your horizontal asymptote is in this example. Okay, so you'll notice that this time as you approach a as you plug in a large value for x and as you plug in a small value for x, you end up getting a function value that's close to 0.5. Now, as you approach positive infinity, the function is actually approaching a half from below. So you'll notice that it's slightly less than a half. Whereas when you're approaching negative infinity, you'll notice that the answer is slightly higher than a half. So it's actually approaching the asymptote from above. Okay. So, and then we're going to look at the intercepts as well. So hopefully this is fairly clear to you. In terms of the x-intercept, we're looking at when y is equal to 0. So we want to know the value of the function when y will be equal to 0. And so if I go up here, actually I'll just write it down here. If I plug in 0 for the function, and I look at x over 2x plus 5, the only way that this function can actually be equal to 0, and in this case it is possible for you to get an answer of 0, the only way that this can ever be equal to 0 is if the numerator is equal to 0. Okay, because then 0 divided by anything will give you 0. So these kinds of rational functions are unique in that sense that it is possible for you to have an x-intercept. And so the only value of x that will make the numerator equal to 0 is 0. Okay. And then for the y-intercept, it's similar to what you've always done. You'd look at f of 0. So plug in x equal to 0 and solve for y. So 0 over 0 plus 5. And that gives me 0 again. And that makes sense because if your x-intercept is at the origin, then your y-intercept also has to be at the origin. Okay. And so finally, we're going to sketch the function. And we'll use the scale of a half again. And so I have my vertical asymptote at negative 2.5, which is here. So x equals negative 2.5. And we have the horizontal asymptote at y equals a half. Okay, and then we can plug any of the points that we know in. So we have an x-intercept and y-intercept at the origin, so that's the only point that we know. And then we can use the end behaviors to help us graph the rest of it. So looking back at our end behaviors, so as the vertical asymptote is being approached from the right, it's approaching negative infinity, so it must be coming downwards. And as the vertical asymptote is being approached from the left, it's approaching positive infinity, so it must be going upwards. And then as the function is approaching positive infinity, as x is approaching positive infinity, the function is approaching a half from below. So as it approaches positive infinity, it's approaching 0.5 from below. And as x approaches negative infinity, the function is approaching 0.5, so the horizontal asymptote from above. So it's sort of doing this. Okay, so you can sort of see parts of my graph being drawn there. And I'm just going to connect it all to get the rest of the function graph. And it'll look sort of like that. Okay, and so this is f of x. Okay, so the last part of the question says, where is the function increasing and where is it decreasing? So increasing means that it's going up and to the right as you go from left to right, and decreasing means it's coming down and to the right as you go from left to right. And so you'll notice that in this case, if you start on the left-hand side of the graph and you move your pencil along with the curve, you'll notice that the function is actually increasing in the first segment. And if you look at the second segment and you follow your pencil from left to right, you'll notice that the function is actually also increasing from left to right. So there are no intervals where the function is decreasing, and the function is actually increasing from negative infinity till negative 2.5, and from negative 2.5 to positive infinity. At exactly 2.5, the function doesn't actually exist. So that's the end of your first segment and then the start of your second segment.